time graphs where the slope of the lines were generally straight, okay, or consistent. And so whenever we had those types of graphs, we knew that the velocity was constant at that particular time. So today we're going to be looking at when we have graphs where the velocity isn't constant. We actually have an accelerating object, okay, as it takes off. Okay, so obviously whenever a plane is taking off, it's not moving at a constant velocity. It's slowly over time, or actually more quickly over time, speeding up. Okay, so the velocity is not constant throughout. It's constantly speeding up or accelerating in order to take off. So there's no straight lines. It does, however, move with a constant acceleration as it flows in a parabolic path. Okay, so you should have heard of like parabolas and stuff in your guys' math classes. So if we examine the position time graph to determine the position of the plane, okay, at first we look at 2 seconds. The position is going to be at 10, and then looking at the units, it's going to be meters west, okay? After 4 seconds, it is at position 40 meters west. And then after 6 seconds, it's at 90 meters west. And then lastly, at 8 seconds, it is at 160 meters west. Okay, so with a curved graph of the line, we can't immediately find the velocity by calculating the slope. Okay, so first we have to draw a tangent line. So hopefully that term tangent line isn't something new to you. It should be something that you've heard in your math class. Okay, so the tangent line is a line that touches the graph at just one point on that graph. So since the slope of a curved graph is always changing, the slope tells us that the instantaneous velocity just at that one point in time, so the slope of that tangent line. So in order to find the instantaneous velocity at time t for an accelerating object, meaning that the position versus time graph has a curved slope, okay, first you'll have to locate the position of the object at time t. Use a ruler or straight edge to draw a line that only touches the curve at that one point. This would be the tangent line. You generally want to kind of draw the ends of that tangent line out a bit just so that you can kind of see what points it touches in order to find the slope of that tangent line. And then lastly, find the slope of that tangent line, like I just said. Okay, so if we were going to determine the instantaneous velocity at the different times given here, we're going to go ahead and work through these, drawing in the tangent lines and then finding the slope of those tangent lines. Okay, so the first one, determine the instantaneous velocity at t 2 seconds. So if we find at time 2, here's our position. Okay, so we're going to draw a tangent line. And it'll be easier for you guys because you guys can actually use a straight edge. All right. And so if we were to go through this, our tangent line okay, we can use this as our triangle here. Okay, so we have to find the slope of that tangent line. All right, so the velocity is rise over run Okay, so our rise, we end at position 20. Okay, that's what's this right here. It's 20. So we're at 20 meters west. Our starting position, so minus our starting position, which was in this case 0 meters west. Okay, and then we'll go through the time. So the ending time would be 3 seconds minus our starting time, which was 1 second. Okay, so we'll get 20 meters west all over 2 seconds. So our final answer will be 10 meters per second west. So that is our instantaneous speed at time 2. Okay, for the next one, determine the instantaneous speed at time 4. So here is the position at time 4. So we're going to draw a tangent line for this. Okay. So about where, like I said, it'll be easier for you guys because you can use a straight edge. Okay, so we're going to find the slope of that tangent line. So once again, velocity is going to be rise over run or change in displacement or position over time. So V equals our ending position, which is here, is 60 meters west, minus the starting position here, which was 20 meters west, all over our ending time, which was 5 seconds, minus our starting time, which is 3 seconds. So whenever we subtract and divide, you should get, well, first when we subtract, we get 40 meters west all over 2 seconds, which equals 20 meters per second west. So that's the instantaneous velocity at 4 seconds. All right, and then for the last one, determine the instantaneous velocity at t equals 6 seconds. So at 6 seconds, our position is here. So whenever we draw the tangent line, okay, there's our tangent line. Okay, so our position, we ended at position of 120 meters west, and our starting was 60 meters west, and then our end time was 7 seconds, our start time was 5. Okay, so plugging that all in, we have 120 meters west, which is our ending position, minus our starting position of 60 meters west, all over the end time minus the start time. Okay, so then we get 60 meters west all over 2 seconds, which equals 30 meters per second west. Okay, so if we look at the 3 different values that we got for the instantaneous velocity, you'll see as time goes on, the velocity is increasing steadily.